Hi, my name is Allison Forrest, and I'm a senior at the University of Houston, Victoria. And for my Introduction to Proofs class, I'll be doing a presentation over what is chapter 15 in our textbook. It's going to be Proofs in Group Theory. And today's theme is going to be my dog. So if you'd like to follow along with pictures of my dog, that's cool too. All right. So the first thing we're going to go over is section 15.1, and that's just going to be kind of basic binary operations and proofs related to binary operations. So kind of a definition of binary operations is it's represented with a little asterisk, and a binary operation, which I will call star, is going to be over a set S, and it's a function that maps every ordered pair of S onto another element in S. And it's referred to as being closed over S if it does this. So that's something like addition. Addition takes two, let's say addition over integers. Addition takes two integers and it maps it to another integer. 3 plus 3 is 6, another integer. So some special characteristics that we might want to be proving about binary operations will be associativity, the identity element, the inverse element, and commutativity. All right. So here's something we refer to as a Cayley table that just represents a set and the binary operation that is applied to it. So if you look at this table here, the binary operation is going to be the star, and then this will be the set applied to the set. So A star A is going to be B, B star A is going to be C, and so on and so forth. So that's just an easier way to look at a binary operation applied to a set S. And here it's obvious to see that every product of the binary operation on a ordered pair is going to be also in the set S, so it is closed. Right? So practicing proving these elements for binary operations, we have the example here. So for a non-empty set S, that we do not know what is in that set, what properties does the binary operation S star satisfy if star is defined as X star Y equals X for all X and Y that are part of S? So the first thing we want to know is this associative? And if it were associative, we can look here at this first definition. X star Y and then star Z would be the same as Y star Z and then star X. So we can see that here X star Y is going to be the same as X, and then star Z is going to be the same as X. And then on the other side here, Y star Z is going to be Y, and then X star Y is going to be X. So because these both sides equal, we know that it is associative for whatever elements do exist in S. So the next idea is to look for a unique identity element. And we can tell here that there's not going to be any unique element E in S, such that for whatever you apply it to, A star E equals A. Now, for the star operation, you can see that whatever element from S you put in the second spot, it's always going to be equal to the first element, but there is no unique element for every element in S is going to be the same. So there's no identity element here, and we've just proved that. The next idea we're going to look at is an inverse element for every unique element in S. So we know that since there is no identity element, there is no element, let's say X inverse, such that X star X inverse equals E. So there's no identity element that we can set that equal to. So we've just proved that there's no inverse here for this binary operation. And now we want to know if it is commutative. So that would mean that X star Y is equal to Y star X. And we know based on the definition here that we're given that X and Y are not equal to each other. So we know it's not commutative. So here we've just used different proofs to prove that it is associative, it does not have an identity element, it does not have inverse, and it is not commutative. So that's just going to be a good example of the way you could use proofs to identify binary operations. So the next section I'm going to cover is section 15.2. and this is going to be over groups and abelian groups. I hope I'm saying abelian right. So groups are going to be binary operations that have some of the characteristics that we've already defined. So it's going to be a binary operation over a set S that is associative, has an identity element, and has inverse elements. And if on top of that, the group is commutative, then it is then an abelian group, which I hope I'm pronouncing that correctly. So an example of this is going to be a set of 3 integers, 0, 1, and 2, under addition. And in this case, we define addition between a and b as a plus b mod 3 so that it stays within the set. So 0 plus 1 is 1, 1 plus 2 is 0 because it's mod 3, so on and so forth. So this is going to be associative. It will have an identity element, an inverse element, and it's also commutative, so it's an abelian group. Right? Some practice here using proofs. We have the example of the set G, which is going to be all real numbers except for -1, which is what this notation right here represents, all real numbers except for -1. And then we're going to use the binary operation here, I'll say star, where star equals a star b equals a plus b plus a times b. All right, so assuming that we know the binary operation is closed on G, which means that for every ordered pair a star b, we know that the product is going to be within the set G. We want to prove that G is a group. Now, when you're going through trying to prove that something is a group, you're going to focus on 3 main parts. You're going to focus on proving it's associative, proving it has an identity element, and proving that it has an inverse element. So for our first proof, we're proving it's associative. So we're going to start with a star b star c, and we want to end up with a star b star c. So we're going to work through kind of the math that we have. So we know that a star b, based on the definition of the binary operation here, it's going to be a plus b plus ab. And then all of that star c, using the definition again of the binary operation, we know that it's going to be all of that plus c plus all of that times c. So if we rearrange all of this again, we can then condense it into a plus b plus c plus bc plus a times b plus c plus bc. And we can again use the binary operation definition here to condense this more into a star b plus c plus bc. And inside this parenthesis right here, we can again use the definition to condense it into a star b star c. So because we've just proven that these two are equal here, we know that it is associative. So we've proven the first part of it. So now we're going to focus on proving that it has an identity element. So this is just going to be an element a star whatever, such that a plus b plus ab equals a. And there's several ways to do this. There's a way that's going to be similar to finding the inverse element, but here it's simply very easy to see that if you use an element a star 0, that it becomes equal to a, because you have the definition here where it's a plus 0 here plus a times 0, which becomes a plus 0 plus 0, which is a. So the 0 is the identity element here. So using a different tactic, we're going to look for inverse elements. So the inverse element a star I, which is I being the inverse of a here, we can use the definition here of the binary operation and say that this is equal to a plus I plus ai. And we know that when we're looking for an inverse element, we want a times its inverse I to be equal to 0. So if we set this definition equal to 0, I becomes negative a over a plus 1, simply solving algebraically. So looking at this equation right here, we know that an inverse I is always going to exist for any element a in G, as long as a is not equal to -1, because if it were, we'd be dividing by 0, which is not something we want to do here. And we know that since -1 is not in our set G here, because it's defined as all real numbers except for -1, then there's always going to be an inverse for every element in G. So now that we've proven that it is associative, has an identity element, and has inverse elements for every member of G, we do know now that it is in fact a group. So we've just proven that the binary operation star over G is a group. So the next section I'm going to be going over is 15.6. We're going to be skipping several sections simply because they're very kind of basic, continuing along the lines of groups. 15.6 is a lot more interesting than some of the proofs that they define in the earlier sections. So we're going to be talking about isomorphic groups here. And what an isomorphic group is actually going to be two different groups. So you have, let's say, two groups, G and H. They're going to be isomorphic if there exists a bijective function, we'll say phi here, that maps G, the elements of G, onto H, and also has the operation preserving function of phi of A star B, where star is the operation on G, equals phi of A star phi of B. So as long as that operation is preserved between the two groups based on the bijective function phi, then they are isomorphic to each other. So we'll get into an example real quick because that's kind of abstract. So over here, looking at the side, we're going to have the set G, and G is defined as ABC right here. And it's going to have the binary operation of star. So here it's defined in this Cayley table that we looked at earlier. A star A is going to be A, B star A is going to be B, C star A is going to be C, so on and so forth. And we do know already that this is a group, which means that it is associative, has an identity element, and has an inverse element. And then on top of that, we're going to have this other group here, the set H defined as XYZ, and it is also going to have a binary operation of its own, plus, and it is X plus X is going to be X here, Z plus X is going to be Z, so on and so forth. And we also know that this is a group, so it is associative, has an identity element, and has inverse elements. All right, so based on that, looking at the Cayley tables, if you're comparing these two tables, it's easy to see that wherever you see an A here in the table for G, the set G, you're going to see an X here in the table for set S. So A, X, X, and there's an A here, which means there's an X here. And then you can see for B, there's always going to be a Z in this table. Wherever you see a C here, there's always going to be a Y in this table. So that's what it says here, is that you can tell from these tables that A corresponds to X, B corresponds to Z, C corresponds to Y. So then if you go on to create this operation preserving function phi, and phi maps G to H, it can be described as this. So phi of A is going to be X, and then phi of B is going to be Z, phi of C is going to be Y. So it just shows you how the mappings move from one table to another. Now we're going to go over a take-home question. So I'm not going to be going over this question's answer in this presentation, but if you would like to understand proofs regarding isomorphic groups, it would be good to go over the answer to this question on your own. So let's let G be a group under multiplication. So we know that the group G under multiplication is associative, has an identity element, and has an inverse element. And then let phi be a bijective function that maps not G onto another set, but G back onto G. And then we'll say that phi, in this case, phi of A, is going to be equal to G times A, where G and A are both elements of the set G. So G times A times, again, the inverse of the original element G. So what we want to do here is prove that phi is an isomorphism that maps G onto G. A hint here for the answer to this question, you will need to prove three things in separate parts. So first, you'll need to prove that phi is 1-to-1. Then you'll need to prove that phi is onto, and then you will need to prove that phi is operation preserving. So once you prove these three things, that will be the full proof for showing that phi is an isomorphism. All right. So that's going to be the end of this presentation. We went over binary operations, groups, and isomorphic groups, and proofs relating to all of those things. So I hope you found that interesting, and if you didn't, I hope you found the pictures of my dog interesting. So, and then again, I would like to say I'm so sorry for my voice. I am sick, but again, I hope you did enjoy the presentation. So thank you for watching.